All right, everybody, this is the second installment in my Bayesian model series. We just saw our A/B testing. This is video number 2. We're going to focus on natural language processing and use a Python Jupyter notebook, of course. And this is number 2 in the series of Bayesian modeling. We're going to have a total of about 5 videos when it's all said and done. Okay, so Bayesian model is basically a statistical model that accepts new information and creates new probabilities of outcomes as new information becomes available. Okay, so as information is constantly output, we pick up this information, incorporate that into our model, and make updates to our predictions. Okay, there's a few different advantages to using Bayesian modeling. We incorporate prior knowledge of the information that was available. As new information becomes available, we quantify that, we ingest that and quantify that. We measure uncertainty, dynamic updating, interpretability, and flexibility. The classic way to look at it is to say, okay, I have an object, and the object is circular. Okay, so what's the probability of an object being circular, or what's given that an object is 90% circular? So we'll incorporate this new, and the object is red, we can predict that this object is an apple. We can take all of these probabilities, 0.9, 0.8, 1.0, and 0.7, multiply them together and get a 54% chance that all of these conditions, right? If it's not circular, not small enough, red, what is the probability? 0.44% equals 1.44% chance that an object is not an apple. Okay, and if the object is an apple, we can multiply all these conditions together and say we are 50.4% certain that an object, an object is an apple, okay. That given that object is not an apple, is not, okay, is or is not, that's what we're looking at here. This is what the A/B testing is about, right? So you have two outcomes, two conditions, A or B. Let's jump into it and see how this works. Okay, so we're going to use a machine learning model right here and look at a condition of natural language processing, or the topic of natural language processing. We're going to import some information from the web. This is basically word index to words, and index to words parsed out. This is available in what is this? sklearn metrics classification report. Okay, and we're going to look at the X training and X testing conditions, and then measure that about against a Y variable or dependent variable. Y, the X variables are independent, the Y variable is dependent, right? And we don't want to measure what is the influence on this Y variable. This is the dependent variable. Given that we have certain independent variables, these are the X variables, right? So I have several videos on my YouTube channel about X and Y variables. X is always the independent, that can be anything, right? It can be anything in the world. The Y is dependent, so it has to be dependent on the X variables, right? Or maybe there's no association or no relationship between those, but that would be weird. Usually there's some type of relationship, right? That's why we do these we create hypothesis and run the machine learning models to see what the relationship is. And if there's nothing, it's nothing, but in most cases, there is a relationship. Otherwise, there's no point in even doing the analysis, right? So here we have the output of this classification report is 83.25% accurate. We can see precision is 0.81, and it's pretty balanced between the zeros and the ones. If we had low numbers down here, we would have to do a smoke sampling technique to get this data set balanced, but it's naturally pretty balanced, so we're all set. If these numbers on the 0 record and these numbers on the 1 record are similar, then they're pretty similar. So we have 12,500 different records that we're measuring, and we can see overall it's pretty accurate, right? So let's go ahead and do a confusion matrix here. The confusion matrix basically is a table that shows you the diagonals. The diagonal numbers should be higher if we, like in the northwest and southeast, if we have big numbers For positive and negative, these are contradictory. That is going to throw off our model a little bit, or the model is getting confused. It's not able to make extremely accurate predictions. If we have positive, negative, again, this is contradictory, but negative, negative, 10, 7, 8, 3, positive, positive, 10, 0, 2, 9. These are fine. We want to see higher numbers on the diagonal and lower numbers on the rest of the matrix, okay? This matrix table or confusion table, confusion matrix, tells us about the performance of classification models by comparing the predicted labels with the actual label, okay? So that's what we're measuring right here. And we can do a receiver operating characteristic curve. So essentially, so I copied this code from online, right? We created a model. Let me refresh this. Okay, and we can look at the RLC curve. Anything that goes from 0, 0 to 1.0 on the diagonal, this will be a random guess. So if this curve, if it's blue curve that curves up to the northwest and then over to the northeast, starts at 0, 0, goes to 1.0, if this curve is pretty close to the diagonal curve, then we can assume that the model is not making very accurate predictions and it's basically just guessing. So 0, 0 to 1.0, 1.0 on the diagonal is a random guess. Anything that has highly curved shape means that the model is making quite accurate predictions, as evidenced over here. We have 10, 783, and 10, 029, positive, positive, negative, negative. So the model is performing pretty well. And based on the curvilinear nature of that curve, that blue line curved, we can say that the model is pretty accurately making estimates and making predictions that match the actual numbers that we're measuring for. That's what we see here, okay? So let's go down a little bit more, create a word cloud. You've probably seen this in one form or another. We're looking at the frequency of all the words in the corpus of words. A corpus is a body of words, right? So we measure the frequency of words shown in the corpus, and the larger numbers that show up have more frequency, obviously, and these get projected into larger text or larger fonts in this word cloud. And any words that show up with lower frequencies or don't show up regularly at all, they have a smaller size in the word cloud, and a smaller font is generated for those. So basically, it jumps off the page that you can see the words that come up over and over and over and over have large text, and the ones that rarely show are going to be tiny, teeny tiny, and barely visible at all. Okay, so bigger the text, more frequency, smaller the text, less frequency. So this is running now. I guess it's taking a little bit longer than I thought. I did this yesterday to prepare for this lecture, but I recall it was running a little bit faster yesterday. We'll give it a minute. We'll give it a minute and come back to that. Let's move on to the next cell, and we can see how this works too. So based on the text that comes to us from this process over here, we're loading data into this classification report, right? We have X training, Y training, and so on and so forth. Based on that, we can introduce some new information over here. Oh, the word cloud is done. So that's nice. So we can see bigger the text, the more frequent the word shows up. And you can see there's a lot of and the. And we can see BR. I'm not sure what the BR means, but anyways, you can see a lot of this is of or the. This in the next level, we would probably eliminate all the words that don't have a lot of meaning to the context of this message. So of and the don't really mean a whole lot. Can't tell what that is referring to, but you would filter out the non-meaningful words. If it's not too useful, we don't need it. We would just get rid of it. If it's more useful, we would keep that and incorporate that into the analysis. Okay, so let's look at one more thing down here. New reviews. I'm adding some more text to this body of text, and I want to see what is the sentiment created based on this text I added. So here's a review. This is a list that I created. The movie was finished. Characteristics were still developed, and the plot was thrilling. So that's something I want to be aware of. I hated this film. It was so boring and predictable. Okay, that's good to know. This, I would say, is positive. The second one is kind of negative, right? Hated this film. Pretty much sounds negative. And an average movie, not great, just average, right? So the first sentiment is positive. The second one is negative, clearly. And actually, average movie, not too bad, but not great either, is actually coming up as negative. I thought that was a little bit neutral. You could have three sentiments, positive, negative, or neutral. The model is saying that this one is actually negative. It sounds a little bit neutral, but it says it's negative. Okay, so Bayes' theorem basically takes updates in the posterior probabilities as it observes new evidence. Okay, and in this case, new words are added to the review. These are the new words that we added in this list. We're iterating through the list for review and new reviews. That's the list that we're looking for right there. If I go to Control F, you can see here's the list, right? And the initial prior assumption was when the model starts, it uses class frequencies and in the process of translating data for the prior probabilities. Okay, so if 70% of the reviews are positive, the prior for the positive class is 0.07, obviously, right? The likelihood of something happening is the process of the words in review, and it all calculates how likely the review it belongs to each class based on the word probabilities and the training data that we're given. Okay, and posterior, so this is prior, likelihood is during, and posterior is after the analysis. After calculating the likelihood, the model produces a posterior probability for each class. The posterior becomes updated belief about the hypothesis after considering all the evidence. Okay, so here's the initial evidence, here's additional evidence, right? So it's making new assumptions, new probabilities, and calculating new outcomes as new data becomes available. So it's pretty cool, right? I like this stuff. It's actually pretty cool. It's pretty interesting. So we have the prior belief. We saw that we have the evidence, and then the updated belief is the posterior. So prior and posterior. Further breakdown, the prior is the probability of a review is positive, might be 70%. Evidence of words in the review, we are looking for positive words and negative words, or positive sentiment and negative sentiment, right? And calculating the probability of something being positive or negative. And then the posterior, again, is the subsequent analysis using Bayes' theorem. We can measure the likelihood of the prior calculations and probabilities of those outcomes that we just saw as being labeled as positive or negative. So that is it, number 2 in the series of Bayesian. So hopefully this was insightful and interesting for you guys and added a little more insight into how Bayesian models work. Thanks for your time and enjoy the rest of your day. Goodbye.